Alright, today we have a really delightful project to work on, actually. Today's video is something I've been looking forward to for a while. This is a kit that recently came in the mail from Sardrimmer. Partly why I've been really excited about this is I think Sardrimmer has an aesthetic sensibility about circuits that's kind of similar to mine. I think we both try to find some space in between the kind of visual beauty and the functional beauty and aim for that. So he has this Boldport club now where every month you can get a kit that will combine art and engineering in some kind of interesting way. So this is going to be project number 1, the tribute to electronics designer Bob Pease. Oh, that's great, it even comes with a sticker. This is really nice. Welcome to the Boldport Club, project number 1. My favorite programming language is solder, a tribute to Bob Pease and an electronics discovery kit based on his LM331 chip. Figure 20, light intensity to frequency converter. It's beautiful, handwritten, signed by Sardrimmer. Numbered 17 out of 180. And the parts for this kit are all in here hidden between layers of cardboard. I think this front piece comes off. I don't want to break it. It's really beautiful how all the parts just nestle in there between the layers of the corrugated cardboard. Oh, there we go. This front piece is just tacked on at the corners. It isn't glued all the way down. So that's how it's meant to open. All right. Oh, there it is. My favorite programming language is solder. Bob Pease. Ah, this feels so delightful. It comes with a little keyring. So this cute little 8-pin chip is the one Bob designed. Got some capacitors. And now that we've got the small parts out, we're just left with the board itself inside this beautiful case. This connector isn't actually soldered on, it's just in there for storage. Oh, this comes with 2 boards. I have one to put together, and then one that I can enjoy in its unassembled state. Let's take a closer look at this circuit board. So you'll probably notice pretty early on that this doesn't really look like a normal circuit board, and it has the sort of facilities you need for it to be electrically sound. So, all the footprints work, and it has all the right manufacturing tolerances, and, the rings around the pads are the right size. But other than that, the traces are really kind of whimsical and very artistically laid out. And I think part of that is due to how Sar also creates his own tools for doing these layouts. He has this PCB layout script called PCB mode, so that he can actually do most of the layout using graphic design tools like Inkscape. And then his tool, PCB mode, handles the kind of electronics manufacturing specific details. So I like that approach where it really sees PCB layout as graphic art first and electrical engineering second, rather than, electrical engineering first and graphics if you're really, really stubborn about it. Because most circuit board layout packages make it really hard to do things like this. So let's take a moment to just look at the datasheet for the LM331 itself. Whoa, it's got a schematic. So this LM331 chip we have is actually specific to the task of converting voltage to frequency. And that might seem kind of weird and niche, but actually I've used this kind of thing before. So a voltage to frequency converter like this is actually pretty useful for applications that need to sense really weak signals that don't change very quickly, because you can convert the voltage to a frequency and then kind of count pulses and integrate that over a period of time. So I've found circuits like this inside of digital scale. I've used circuits like this in the past for making kind of spectrometer equipment. It's a pretty nice way of getting kind of arbitrary precision analog to digital conversion. Here's the pinout. We've got a frequency output. This wide dynamic range is actually one reason you'll see people use a voltage to frequency converter instead of a traditional A to D. Since with the same electronics, you can sense very different levels of signal intensity by adjusting your integration period when sampling the resulting pulses. So if you built, for example, a light sensor around this chip, you could adjust your exposure by just controlling the time window in which you're counting pulses from this voltage to frequency converter. Then you could use that to get a very wide range of different input voltages out of the same circuit. 100 dB is 10 orders of magnitude. It takes a pretty amazing amount of analog electrical engineering mastery to create something like this. So definitely hats off to Bob Pease. It's pretty amazing the kinds of things you can do when you're designing silicon. I just want to make transistors that share a base and each have like 4 collectors. You can do that in silicon. It's such a strange universe. I'd really love to see this world of design more open to hobbyists. Like, the approach that you have to take when designing a circuit like this must be just so different from, designing something using off-the-shelf parts. It isn't immediately obvious which side is supposed to be the component side and which side is supposed to be the solder side, since so many of the components are reversible. But you can tell that, if this were the top side, then the pin 1 marking on the chip wouldn't be possible. So this has got to be the top side. So to find out which resistors go where, we can look at either the schematic on the front of the kit, or actually the silk screen on the back of the board includes all the component values too. That's super handy. I really like the handwritten style too. Another detail I enjoy is that so many of the components here include provisions for either through-hole or surface mount parts. So even though this kit includes all through-hole parts, you could assemble this using surface mount resistors and surface mount transistors. So let's take stock of the resistors we have. I know for some people resistor color codes are hard, and for some people they're easy. I feel like I've been doing it for so long that some of the colors just kind of almost have this synesthetic sense to them. Like, I get that about the first few. I don't always remember which one is, blue and which one's violet, but the brown, red, orange series for 1, 2, 3, that just feels, it just kind of makes sense at a gut level. So this one, I could tell you right away, is 10K. And if you look at the schematic, there is indeed a 10K right over here. I think this 10K resistor actually works in combination with that 1 nanofarad capacitor to form the time constant for the input in the circuit. So when light hits this phototransistor, it causes a current to flow, a photocurrent. The base on the transistor is shown disconnected like this, but it almost acts like the light itself is acting as the current into the base would. So the photocurrent flows through here, through this series 10K resistor that I'm about to install. And so I think that is actually what sets the rate of discharge for this 1 nanofarad capacitor when the light's hitting this phototransistor. So this resistor probably actually controls the sensitivity of the circuit at the input side. Here's some more of those friendly oranges and browns. This one's actually an old favorite of mine. If I was allowed to have like a best friend that was a resistor in elementary school, it probably would have been this one. The reason I remember 330 ohms so fondly is that this is, actually I suspect it showed up in some early schematics, like maybe some Forrest M. Mims books for driving LEDs. Because it's a pretty good series resistor value to use for driving LEDs off of 5 volts or so. And so somehow that color code, the friendly orange brown, kind of just really seemed warm and cozy to me growing up. All right, that's the next resistor installed. Just another power of 10. So this one is orange, orange, red. So this one's 3.3K. So this one's being used as a pull-up resistor on the output, it looks like. So these next two resistors look like fancy high-precision resistors. These should be the 6.81K and the 5K resistor. Yeah, this must be a fancy precision resistor. So there we've got 6.81K, and that's pretty close to 5K. Just making sure all the components are sitting flat. So normally I would just solder the resistors kind of right at this point, but I think because I want this board to be as beautiful as I can make it, I will spend a little bit more time on prepping these for the best solder joints possible. So first of all, I just want to make sure these resistors are sitting very flat against the board. So normally you would trim these after soldering, but I'm going to try a slightly different technique from Sar himself to try to get the nicest joints I can. All right, safety glasses this time. And I'm going to trim these all very close to the board, so maybe like 1 millimeter. These resistors are all little springs that want to jump out of their holes. I'm adding a little bit more solder than you normally would just to make the joint round. And that's mostly to avoid sharp edges. I mean, you could sand them too, but then that creates lead dust, which I like to avoid. Alright, so all the resistors are soldered in. I can take this tape off. I'm going to touch up the front of these joints too. For the misbehaving solder, I've got some of this water-soluble flux. Super handy. Much better. This is, of course, completely aesthetic. I just want the tops of these joints to look nice too. So if I add some flux and then reflow the solder, then they should have a nice even coating rather than the kind of spotty coating they had before. The capillary action here is really strong. Like even on these joints that appear to have no solder, with a little bit of flux, it wicks it up right from the backside of the board. Flux is really magical when you're working with solder. This is a little bit ragged on this side. So I think next I'm going to put in this connector. Just in order to make sure that the connector is seated fully against the board, I'm going to apply pressure to the middle right here while I melt this solder joint. So now I've kind of locked in this mechanical position with the connector fully seated. And now I let that one cool. And then if I solder all the other joints, then it'll reinforce that position I've locked in. And then I can go back and resolder that first joint properly. Great, so now the USB connector is fully soldered on there and nice and parallel with the rest of the circuit board. And still quite warm. So this variable resistor is in what looks like a pretty normal through-hole package, but the leads are already bent outwards at a 90-degree angle like that. So while it's probably possible to unbend them and use this as through-hole, it's clearly intended as a surface mount chip. So let's attach it that way. I wanted to tack it down quickly on the first pin just to make sure I had the angle right. And then go back and add more solder. So that's where the transistor goes, and it looks like you can use either a surface mount or a through-hole transistor. So the kit comes with 2 of these through-hole capacitors, and it looks like we need a 330 picofarad and 1 microfarad. And these happen to be labeled 331 and 102. But let's just double check with a capacitance meter. So my eBay special LC meter here is reading 435 picofarads for the capacitor labeled 331. And for the other one labeled 102, I'm actually reading around a nanofarad. Oh, okay, 1 nanofarad is right. The schematic here says pretty clearly 1 nanofarad. I was just misreading it on the board. I thought it said 1 microfarad. I'm just going to cut off the sticky part. I always hate how this tape the parts are packaged on. It just makes the lead sticky. The capacitors are preformed a little bit, but not quite enough for this particular layout. So I'm going to bend them out just a little more. That's about right. So this time I'm just going to try tacking them on with a little bit of solder. Then I'll trim them and go back and make the joints nice. Remember your safety glasses, kids. And this time I think there's enough flux in here that I won't have to add any. That's great. I'm also noticing that the back of the variable resistor here is kind of partially filled with solder. So just for consistency, I'm going to fill in those two. I'm pretty happy with those resistors and capacitors. I think it's time to put in the LM331 itself. So I'm going to preform the leads just by bending them slightly. You can get tools to do that, but no one ever does. There it is. I'm going to ever so slightly bend. Alright, so pin 1's in the right place. It's on the right side of the board. It's always important when you're using one of these side cutters to only cut 1 pin at a time. If you try to save time and, try to cut more than one thing at once, then you'll actually use the 2 things as kind of levers to pry each other apart. It's not good. Ah, that feels great. No sharp bits. All nice and smooth. So what's left? We have a 2N7000, which is a MOSFET transistor. We also have a green LED. Whoa, this is a really retro LED. This LED is really unique. I've never seen anything quite like this. It looks like a normal kind of 5mm LED at first, but then this ridge where normally you'd have kind of a bit of a flange with a D shape on it, here it's all just cylindrical. That's really elegant. I'm going to test this LED with a battery just to make sure I know what the orientation is. I wouldn't want to get that backwards. Usually, if you look inside the LED and you catch the light just right, you can see that one of the legs is connected to the little cup that supports the actual LED chip. And usually that one's the minus the cathode on the LED. That looks great, a nice soft green glow. Really, all LEDs used to look like this. The modern high brightness LEDs are quite a bit different than old school indicator LEDs like this one. That's great. So the LED then does follow our expectation where the lead frame here and also the shorter lead is the cathode and the longer lead is the anode. So this one also needs a little bit of bending to fit the right width. There are a couple of ways to verify the polarity on the board here. The symbol for the diode is here, and the dashed end is the minus on the LED, which is kind of a useful mnemonic. You can also follow the schematic and see that the positive leg of the LED will go right over here to the 330 ohm resistor, and then to the positive 5 input from the USB. whereas the negative leg of the LED will end up switched by the MOSFET over here. All right, LEDs attached. I'm going to clean up a few more of these top side joints. All right, just two more parts left. We have a phototransistor and a regular transistor. Well, there's nothing regular about a MOSFET. MOSFETs are pretty awesome. And these two might need a little bit of research in order to see which direction around they go. The datasheet for the 2N7000 FET has a helpful diagram here. According to the internet, this is a convention. The flat spot on the side or the shorter pin should indicate the emitter on a phototransistor. And the emitter is the one with the arrow pointing out of it. I think that's the right way around, but I'm going to see if I can actually test this before soldering it in. Just kind of holding it against the plating on the board. That's the reason why I put this in last. If you're at all interested in this kind of a circuit, I would highly recommend going through the datasheet. It's pretty interesting. So this block diagram gives us a simplified idea of how this circuit is designed to work. So the input is based on a comparator, which looks at two voltages and kind of quickly swings from one output rail to the other based on which voltage is higher and which one's lower. So you can think of it as a differential amplifier with very large gain. So it's like it's taking the positive input and subtracting the negative input, and then kind of multiplying that by an arbitrarily large number, and then limiting that to the actual supply rails, the voltages available. And so that's what this comparator is doing. And in effect, this is being used as part of a feedback loop to match these two inputs by kind of delivering these little current pulses into this resistor capacitor circuit. So this one-shot timer here generates pulses of a particular controlled length. So that has two outputs, one providing the actual output for the LM331, and then one going back here as a negative feedback for this entire circuit. And that feedback path switches these little controlled current pulses into a resistor capacitor circuit here. So as this input voltage changes, it changes the set point that this resistor capacitor network has to reach in order for the one-shot timer to go and send another corrective current pulse into it. So then a bit further down in the data sheet, there are a bunch of examples. And in fact, sure enough, when we scroll down to figure 20, we can find the exact schematic that the Boldport Club kit package has printed on it. And in fact, it isn't quite exact. In this schematic, the output is just kind of going off into space. On the Boldport packaging, there's a little dotted line indicating the separation between the original schematic and the FET and LED that just provides some visual output. All right, well, that should be the end of it. Let's get the extra flux residue cleaned off this board. Nothing like isopropanol. That side's looking good. Gotta be careful with those transistors. Like splay out all over. I do like surface mount, but the dip is pretty nostalgic. Alright, that seems pretty unfluxed. Well, it looks like we've got a finished board. Check that out. Boldport Club, project number 1. Let's try this circuit out. Oh, there it goes. Glowing green. Nice old school LED green glow. Drawing 13 milliamps there, seems about right. So if we adjust this potentiometer, nothing too obvious just yet. I don't know if we'll be able to notice the change in frequency just by looking at the LED brightness, but let's try hooking this thing up to the scope. And I'm going to take the output from this leg of the pull-up resistor. Alright, well I think here we've got our demo. So if I zoom in a lot, we can see that the pulses are always about 3 microseconds. I have the scope set to trigger on the negative edge there. But the time between pulses jumps around a lot, and that's actually noise in the incoming light signal. With this kind of integrator circuit, you can easily filter out the noise just by counting pulses for a longer period of time. The dynamic range of this circuit is pretty impressive. With the phototransistor covered up, I can get the frequency as low as around 120 hertz. Yeah, just with the light from this desk lamp here, now I'm getting around 900 hertz. If I point a flashlight into the sensor, I can get that to go way higher. Yeah, that's around 6.5 kilohertz. That's around 22 kilohertz. That signal happens to be conveniently in a good frequency range for audio. I wonder what this sounds like. Alright, so I have this box, which is really just an audio transformer and a little ballast resistor, so that I can get a line out from something that's more speaker-like. So this kind of controls the bass tone that you get for any particular light level. Well, I hope you enjoyed putting together Boldport Club project number 1 with me. This is a really aesthetically pleasing object on its own, but it also has this really interesting story to tell about the LM331 chip and its many, many talents. And we already know that this can detect light levels over a pretty wide range of brightnesses, and it can make some noise. I wonder what else it can do. If you have any other ideas, let me know in the comments. And if this seems like your kind of project, then check out Boldport Club. You can still join, and you get 1 project every month. So I hope you enjoyed this video. If you liked it, maybe check out some of the other videos I have, and subscribe so you'll be the first to know when I post something new. Thanks, and keep hacking.